Good day, stat students. So today we're going to go over section 9.3. We're going to do a hypothesis test for means. And so what has changed from section 9.2? Well, what's changed is the data from 9.2 was categorical. So when you have categorical data, you're going to use proportion to analyze the data. However, when the data is quantitative, which we're running into a 9.3, okay? So 9.3, the data is quantitative. And what are we going to do then? We're going to use a mean, not a proportion or a percentage, to analyze the data. Okay? So step one, state the hypotheses. Parameter that will be tested would be the population mean, mu, not the population proportion, p. That's obvious. Okay, and we've talked about how to state these, meaning the null and the alternative hypotheses before. We practiced it, and so the null will always get the equal to sign. The alternative will either get greater than, less than, or not equal to, depending on the situation. Step two, verify the conditions or assumptions. All right, so unlike the population proportion p, the conditions are exactly the same as a confidence interval for mu. So if you look back with regards to a confidence interval for p and a hypothesis test for p, there are slightly different conditions. All right, that's not the case for mu. The confidence interval and the hypothesis test have exactly the same conditions. All right, they have exactly the same conditions. Nothing new to memorize here. Okay, so let's review them. The data are obtained using a random sample or experiment, or we did an experiment. 2, the data does not have extreme outliers. And then 3, the sampling distribution of x bar follows an approximately normal distribution, aka a t-distribution. Okay, remember, t-distribution is an approximately normal distribution. So what would make the sampling distribution of x bar follow a t-distribution? Well, you need one of two things. Either one will do. Either we need x to be normal, okay, and that's important if n is less than 30. Why? Because if n was greater than or equal to 30, then what could apply? The central limit theorem could apply. All right. So we need either this one or we need this one, okay? And if we want you to use this one, okay, we're going to have to state that in the problem. Step 3, what about the test statistic? The test stat measures how far the sample mean, x bar, remember that's x bar, right, falls from the null hypothesis value, which we're calling mu sub 0, as measured by the number of standard errors between them. So let's take a look at the formula. Okay, so the numerator measures how far away x bar is from mu sub 0. That's the numerator. By doing that subtraction, that's what we're doing. But how many standard errors is that? Which is the denominator. Okay, so when you put this in your calculator, all right, when you put this in your calculator, I would go ahead and maybe just do all this at once. That would probably be fine, but you need parentheses, both the numerator and denominator. Okay, so as long as you put parentheses in both, you should be okay. And going forward, I'm probably going to put a little TS down here to stand for test statistic. Okay, make sure that we understand the difference between the test stat and the critical value. Step 4, calculating that probability value, or that p-value. All right, it describes how unusual the data would be if the statement in the null was true. All right, so no different definition than before. All right, since we're using the t-distribution, we need degrees of freedom, and the degrees of freedom is still n minus 1. Now, here's the thing, is that with the t-table, because the t-table, okay, is just some, if you will, some highlights at every degree of freedom, it's really hard to calculate an exact p-value from a t-table, okay? And so all you can do is estimate the p-value using a t-table. Okay. However, when you do your homework, when you're working in WebAssign, you will need to enter an exact p-value. Okay. And so how are we going to do that? We're going to use StatCrunch to do that. Okay, so for homework, okay, so for homework, we're going to go ahead and use StatCrunch to figure out our p-value. Okay. Um, on the test, if we want you to continue this problem, we would have to give you the p-value. All right, and um, and so and the test is actually going to be a little easier because we'll say, okay, let's run through the hypothesis test, and maybe you'll have to state the hypotheses, do the conditions, calculate the test stat, and then we're going to say, oh, here's the p-value, okay, and then we'll have you do the conclusion on the exam. All right. So the conclusion, no different than what we did with the population portion p. If the p-value is less than or equal to alpha, we're going to reject the null, and we're going to say we have strong evidence that HA is correct. And remember, we got to put that in terms of the problem. And if the p-value is greater than alpha, we would say do not reject the null, and we would start our statement as we do not have strong evidence that HA is correct. That's it. Okay. So there's not that many differences, and this is the exact same 5 steps. All right. So here's example 1. A medical researcher, after several years of general observation of her patients, thought that it was possible that the mean temperature of all healthy humans is actually less than 98.6 degrees Fahrenheit. She takes the temperature of 81 randomly selected healthy humans and finds that their mean temperature is 98.5 degrees Fahrenheit, with a standard deviation of 0.3 degrees Fahrenheit. Test her claim at a significance level of 0.05. Believe it or not, this was actually done as an experiment by medical researchers at the University of Michigan. I didn't necessarily use their data, okay, but they actually did test this, okay. All right, so let's run through this. So the variable, notice the variable here. It's temperature of healthy humans. That's quantitative, right? Temperature, quantitative, it's a number. All right, so what are we going to do? We're going to use mu to understand stuff, okay, to analyze this data. So what was the sample? 81 healthy humans, right? So n is equal to 81, degrees of freedom is 80. So if our sample was 81 healthy humans, what's our population? All healthy humans. Seems reasonable. Sample mean, what was the sample mean? It was 98.5. And so how do we get that? Well, we had the temperature of 81 healthy humans. We averaged those numbers just like we did in chapter 2 to figure out X bar, okay? And we're just already, we're pretending that we already had that data, and we've already calculated the mean, and there's your sample mean. Turned out to be 98.5. Okay, how about the sample standard deviation? The sample standard deviation, what did that turn out to be? That turned out to be 0.3. Okay, so that's S in the problem. I probably should have put that, but that's S. There we go. Now I did. Significance level. We might as well state that. That is, remember that's alpha, and that's 0.05. Okay, right there. Significance level, 0.05. Okay, so let's go through the problem. State the hypotheses. So we would start with the alternative. And so what was she testing? She was testing if, let's see, she takes the temperature, right up here. I'm sorry, I was reading the wrong line. She wanted to test if the mean temperature was actually less than 98.6 degrees Fahrenheit. So she was testing if mu was less than 98.6. What's the null going to be? Mu is going to be equal to 98.6. That means mu sub 0 is 98.6, right? It's the value in the null hypothesis. Step 2, confirm the conditions, or the slash assumptions. All right, so let's see here. Let's see, she takes the temperature of 81 randomly selected healthy humans. So random sample was taken, check mark. No mention of extreme outliers in the problem. So how would we determine if we had extreme outliers? We would go ahead and maybe make a histogram or a dot plot see if there's any observation way out there. We might have to go ahead and uh, um, see how many standard errors that is from everybody. Things like that. Okay, that's what we would do. In if we were doing this in real life and not in an academic setting. Okay, so no mention in the problem of extreme outliers. 3. Since n is equal to 81, which is greater than or equal to 30, the central limit there applies. And the sampling distribution of x bar, remember that's our way of saying that, and the sampling distribution of x bar is approximately normal distribution. I probably forgot the word n here. Is an approximately normal distribution, which that's pretty much the definition of what? A t-distribution. All right, so we're seeing that the sampling distribution of x bar follows a t-distribution. Fantastic. Step number 3 then, calculate the test statistic. All right, so let's see, the sample was 81 healthy humans, n is equal to 81, and so x bar is equal to 98.5, sample standard deviation is equal to 0.3, remember that's S in the problem. Okay, and remember that the null hypothesis had mu is equal to 98.6. All right, so you throw that stuff in the computer, excuse me, not the computer, in your calculator. And remember, when you do that, parentheses, right? Parentheses. I didn't draw them here, and that, actually, if you take a look at any textbook, they're not going to put the parentheses here either. Okay, you just got to realize that they're supposed to be there. Okay, when I figured this out, it came out to a negative 3.00 rounded to 2 decimal places. That's probably good enough. Okay. And again, let's remember that this is a test statistic. Okay. Okay. So we have our test stat. The p-value is the area to the left of t, which was equal to negative 3, with 80 degrees of freedom. Okay. So we have now, why did I say left of t? Well, because we have a less than sign in the alternative, so we have a left tail test, don't we? We have a left tail test. Okay, let's depict that. And so this is the t-distribution. All right, our x bar fell over here, and that was at 3 standard errors away. The computer depicted it with that area right there. So remember, the total area underneath this curve is 100%. How much area did we just carve out? Not a whole lot, right? So this is the p-value depicted by the red area right there. So you would go into StatCrunch, okay, and it's fairly simple. Remember, you would go to into calculators, okay, and go find the t-distribution, right? And so, you know what? How about this? Maybe I'll show it to you right here. Okay, I'll show it to you right here, and that wouldn't be a bad idea. Let's see here. We'll discard. We'll go over to StatCrunch. So you would go to Stat Calculators. Okay, Stat Calculators t-distribution. Stat calculators t-distribution. Okay, to figure out this p-value. Okay. All right. So we had it defaults to 10 degrees of freedom. We'll put in 80. All right. Since it's a left-tailed test, we'll put a less than sign there, and this is where our test statistic goes, right in here. Okay. So our test stat goes right in here. So we got 80 degrees of freedom. And we'll put in a negative 3, less than, compute. This is our p-value right here. Okay, that's our p-value. So it looks like our p-value is 0.0018. 0.0018. So fairly small p-value, right? Small probability. Okay, that seems reasonable based upon what we depicted over here. Okay, So 0.0018. Alright, so I think we can get back into our, and right here, notice in the slide, p-value is 0.0018. Okay? So let's see, let's get back into the slideshow. Okay, and there we go. Okay? Alright, let's see, so we have our p-value. What do we always compare that to? Alpha, right? Alpha was set to 0.05 in the problem. So, conclusion, the small p-value of 0.0018 provides considerable evidence against the null hypothesis. Why? Because the p-value is less than alpha. So basically the probability of all this happening is really small. And what does that say about the null hypothesis? It's probably wrong. Okay? That means the alternative is probably correct. Okay? So we're going to reject the null. Okay? And what are we going to say? When you reject the null, we have strong evidence. Okay? Remember, we started off like that. We have strong evidence that the mean temperature of all healthy humans, which is, oh, I got to get my pen back out. So right here, the mean temperature of all healthy humans, what is that? That's mu. Okay? So all we're simply saying is that we have strong evidence that the mean temperature of all healthy humans, which is mu, is less than 98.6 degrees Fahrenheit. Okay? And that was it. Alright? So, let's go on to the next problem. So an administrator at the University of Akron is concerned how long it takes students who commute to find a parking space once they get to campus. He wants to test whether it takes more than 300 seconds, meaning 5 minutes, to find a spot once on campus. He randomly selects 100 commuters, and the mean time for them to find a parking spot is 310.4 seconds with a standard deviation of 80 seconds. Test the claim at a significance level of 0.05. Okay, so what's the variable? Time to park, right? That's quantitative. It's a number. So our sample, we had 100 UA commuters. So n is equal to 100 degrees of freedom would be 99 in this situation, and minus 1. What's our population? All UA commuters. If we looked at 100 UA commuters, well, that means our population had to be all the UA commuters then. It only makes sense. Sample mean. Let's see. We should be able to get that from the problem. So he randomly selects 100 commuters, and the mean time for that sample, that's x bar, is 310.4 seconds. Sample standard deviation is equal to 80. So if you keep on reading there, okay, it's 80 seconds. That is S. That's supposed to be an S, not a 5. Okay. So, and the significance level is what? 0.05 again. Okay. So there's your background information. I think we can go through the 5 steps now. Step 1, state the hypotheses. And so what was the administrator testing? Let's see. It was a he, so he wanted to test if it took more than 300 seconds, right? So mu is greater than 300. What would be the null? Mu is equal to 300. And if that's the case, that means mu sub 0 is equal to 300. Step 2, confirm the conditions / assumptions. All right. He took a random sample. 1, check mark. All right. Right here. Okay. 2, no mention of extreme outliers. 3, since n is equal to 100, which is greater than or equal to 30, the essential limit theorem applies, and the sampling distribution of x bar is, again, I forgot, I probably copied it from my last slide, is n, an approximately normal distribution, meaning the t-distribution, right? So the sampling distribution of x bar follows a t-distribution. Okay, step 3, calculate the test statistic. So let's see, we had n is equal to 100, we had an x bar of 310.4, we had a sample standard deviation S of 80, we had a mu sub 0 of 300, and I think we have all of our pieces parts. So we're going to see how far x bar is from the value of the null hypothesis in terms of the number of standard errors. So again, this is a test statistic, okay, and we'll go ahead and put parentheses here, we'll put parentheses here when you put it in your calculator, okay. That should work just nicely when you figure all that stuff out, okay. So that's actually fairly easy to calculate the numerator and denominator. 310.4 minus 300, well, that's 10.4 if you take a close look at that. The square root of 100 is 10, so 80 divided by 10 is just 8. So I calculated a test statistic of 1.30. 1.30. Okay. So how about we do this? How about we do the interpretation of the test statistic? We didn't do that in the last problem. I probably should have. Okay. So what is that telling us? Is that our x bar was 1.3 standard errors above the value in the null hypothesis. Okay. So when we can interpret the test statistic, we probably should. I probably shouldn't have skipped it in the last problem. Okay, but that's what's going on there. If you need to go back to the last problem, remember that was a -3 for the test statistic, so that's telling us that our x bar was 3 standard errors below the value in the null hypothesis. Okay, all right, let's move on. P-value, right? So we got a right tail test because we have a greater than sign in the alternative. So we're going to figure out the area to the right of our test statistic of 1.30. And we have 99 degrees of freedom. Okay, so let's go ahead and do that. We'll do it once more. 1.3 and 99. Okay, 1.3 and 99. So 99, 1.30. Be careful, we want greater than. And so when we calculate it, it turned out to be 0.0983, 0.0983, rounded to 4 decimal places. So remember, don't just chop this off. If this fifth decimal was 5 or higher, we would round it up. But since it's 0, we'll just leave it as 0.0983. And there's our p-value right there. Okay. All right, moving on. What do we always compare the p-value to? Alpha. So the p-value of 0.0983 does not provide considerable evidence against the null hypothesis, as it is greater than 0.05. Therefore, do not reject the null. Remember, don't accept the null. That would be incorrect. Meaning again, the statements in the null and the alternative hypothesis are both still plausible. So that's why we don't accept the null hypothesis, because the alternative is also a possibility. Okay, and so we can't just go ahead and accept the null, because we're saying, well, the null is a possibility, but guess what? So is the alternative. Okay, that's why we don't accept that null. So how are we going to state our conclusion? Since we said do not reject the null hypothesis, we're going to say we do not have strong evidence. We do not have sufficient evidence. We do not have statistically significant evidence. Remember, the nots go together. The do nots go together. Okay, when you say do not reject the null hypothesis, we would say we do not have strong evidence that the mean time for all UAE commuting students to find a parking space is greater than 300 seconds. So that's just our silly way of saying, well, we don't know which one is correct. Okay, and actually, what's really going on here is that mu could be greater than 300, it could be equal to 300, and guess what? It could also be less than 300, and we don't know which one it is at this point. Okay, and so that's what's going on here. Okay. So to me, when you test mu, it's actually a lot more straightforward. Okay, a lot less to do versus testing the population portion P. Okay. The last thing that I want to bring up to you guys. Okay. So the last problem, the p-value was 0.0983. Now pay close attention to what I'm saying here. If the problem was a two-tailed test. So if HA, the alternative, has a not equal to sign. It didn't, but let's just pretend it did. So let's pretend that we're running a two-tailed test, okay? What we would have had to do is we would have had to multiply 0.0983 by 2 to actually get our p-value, because remember, you're testing both the less than and greater than. And so once you find the one tail, if you're working with a probability distribution that's perfectly symmetrical, you would just multiply it by 2 to go figure out that p-value then. Okay? And so if that problem was a two-tailed test, we would have had to take 0.0983 multiplied by 2 to get 0.1966 for our p-value. All right? So that's what you got to do if you had a two-tailed test. Figure out the one tail, multiply by 2. Okay? So I just wanted to point that out because we're not going to do any more problems with regards to testing mu. All right? So if you run into a two-tailed test, that's what you got to do. Okay? That takes us to our end of our presentation. Thank you for your time today.